Prior to the 1st of July 2025, I believed astronomers had a firm grasp on interstellar travelers. My understanding was based on two prior instances, well-defined theoretical frameworks, and technology seemingly equipped to unravel any enigma the universe presented. However, the arrival of 3I Atlas caused our certainty to dissipate as swiftly as ice under the sun's rays. The more I investigate this object, the less it seems to conform to logic. It generates carbon dioxide at a volume that should be physically unattainable for its dimensions. It sustains gaseous clouds that stretch out beyond the scope of Earth's own path around the Sun. It exhibits chemical fingerprints that are inconsistent with any formation scenario I can conceive. Every fresh observation compels me to challenge principles I had considered established science. The most formidable telescopes on the planet are, in effect, conceding to a piece of rock and ice that is hardly bigger than a small municipality. What conclusion can I draw when my most advanced science is unable to account for something as fundamental as a comet? I invite you to join me as I delve into why this visitor could signify either the most significant finding of my generation or evidence that the cosmos still guards secrets I am not yet equipped to comprehend. Part 1. Why 3I Atlas simply defies explanation. On the 1st of July 2025, at exactly 14 hours and 37 minutes Universal Time, an event altered the course of my cosmic comprehension. It did not happen in a remote galaxy or within the theoretical constructs of scholarly articles, but right in my own solar system. The Atlas Survey Station in Chile, an automated telescope on a routine scan for asteroids that could pose a threat, recorded something that ought not to be. The object materialized as little more than a faint blur against the starfield, a moving point at 4.5 astronomical units from our Sun's location. Yet, in a matter of hours, orbital analysis confirmed a fact that sent shockwaves through the astronomical field. This traveler was moving along a hyperbolic path with an eccentricity far exceeding one. In the lexicon of celestial mechanics, this signifies it is unbound, destined never to revisit our solar system. It was designated C-2025N1 Atlas. But for me and others who study the wanderers from between the stars, it was known simply as 3I Atlas, the third verified interstellar object to visit my cosmic vicinity. Its velocity alone should have been my initial indication that I was observing something truly exceptional. 130,000 miles per hour, or 209,000 kilometers per hour. That is not merely fast by terrestrial measures. It represents the swiftest solar system visitor I have ever documented. To give this context, picture a bullet moving at its usual speed. Then increase that speed by a factor of 170. That is 3I Atlas, hurtling through space with the kinetic energy of an entirely different star system. But I would soon learn that its speed was just the start of its enigmas. Within days of its discovery, the Gemini North Telescope in Hawaii aimed its 8-meter mirror at this cosmic trespasser. What it uncovered defied my expectations for an interstellar fragment. There, encircling the invisible core, was a hazy, dense coma, a cloud of gas and dust actively being liberated by solar warmth. This was not some inert, lifeless piece of interstellar rubble. This entity was active, exhaling vapor into the void as our sun's warmth roused dormant ices that had been in a state of suspended animation for millennia in the cold expanse between stars. The implication struck the scientific community with the force of a meteor. Here was an object that had journeyed through the galactic wilderness withstanding radiation that would sterilize any terrestrial life form and enduring temperatures only a few degrees above absolute zero. Yet, the instant our sun's heat reached it, it started to sublimate, to change directly from ice into gas, forming a spectral atmosphere in the vacuum of space. But what was perhaps most disquieting was what this activity signified about its orbital trajectory. 3I Atlas was not just traversing my solar system, it was navigating the space between planetary orbits with uncanny precision. Its nearest pass to Earth would be 1.88 astronomical units, approximately 270 million kilometers. A safe distance, certainly, but the geometry felt almost too opportune, too perfectly arranged for my observation. NASA promptly mobilized its most powerful assets: the Hubble Space Telescope, the James Webb Space Telescope, the Swift Observatory, and the Transiting Exoplanet Survey satellite. The European Space Agency coordinated a global tracking initiative. This was more than just another comet for my catalog. This was an emissary from a different stellar system, bearing chemical signatures that could unveil the conditions within an alien planetary nursery. And yet, even as the world's most sophisticated telescopes directed their focus toward this visitor, a disquieting trend materialized. Every observation appeared to generate more questions than it resolved. The object's conduct did not align with any current model of interstellar debris. Its chemistry challenged the conventional understanding of comet composition, and its very existence in my solar system, moving at such an extreme velocity while remaining active, pointed to formation circumstances unlike anything in my local cosmic surroundings. The irony of the situation was not lost on me as I studied it. Here was an object from light years away, a distance beyond what my imagination could truly fathom. Still, it would spend the subsequent few months within the relatively known confines of my solar system. It was a cosmic guest, staying just long enough for me to study, yet moving so rapidly that each observational opportunity was precious and brief. As July gave way to August and the initial detailed images started to arrive from my most advanced instruments, one fact became undeniably clear. 3II Atlas was not going to reveal its secrets with ease. If anything, the more I discovered about it, the more enigmatic it grew. The scene was prepared for a pursuit against time itself, a competition to comprehend this mysterious wanderer before it vanished back into the cosmic blackness forever, taking its secrets back to the void between the stars. Part 2. The Path Through Our Neighborhood. I imagine the solar system as a great clockwork mechanism, with planetary orbits tracing foreseeable routes through space and time. Now I envision a projectile launched from another galaxy, racing through this cosmic apparatus at an incredible speed, weaving between the gears with mathematical exactness. That projectile is 3I Atlas, and its course through my neighborhood narrates a story of cosmic timing that is almost dramatic. The visitor's schedule reads like a meticulously organized tour of the inner solar system, yet it was inscribed in the stars long before Earth came into being. Perihelion, the closest point to our Sun, was calculated to occur on the 29th of October, 2025. Not at the comfortable range of most comets, but a fiery transit between the orbits of Earth and Mars, roughly 130 million miles from our star. It would be close enough for the Sun's energy to vaporize ancient ices, yet distant enough to prevent its utter disintegration. But it is here that the cosmic choreography becomes almost cruelly precise. As 3I Atlas makes its closest approach to the Sun, Earth will be positioned on the diametrically opposite side of our star. For nearly 2 months, from late September through early November, our visitor will be lost in the Sun's brilliance, invisible to every telescope on or orbiting Earth. It is as if the universe conspired to conceal the most crucial moments of this interstellar meeting. The observational window tells a story of astronomical frustration. I realize scientists have about 3 months to collect data before 3I Atlas disappears behind our star. Then, perhaps 6 weeks after it reappears in December, before the object becomes too dim and far away for meaningful study. It's a deadline that would make any investigative journalist anxious. Except these journalists are studying something that will never return for another visit. Yet, the trajectory offers tantalizing opportunities for those of us willing to think beyond Earth's vantage point. On the 3rd of October, 2025, 3I Atlas is set to pass Mars at a mere 29 million kilometers. That is nearer than Mars' own moons approach the planet. For the robotic fleet orbiting the Red Planet, including the Mars Reconnaissance Orbiter and its powerful high-rise camera, this offers an unparalleled opportunity to capture an image of an interstellar visitor from an alien perspective. Geometry is paramount in astronomy, and this geometry is both a blessing and a curse. When 3I Atlas reappears in Earth's skies in early December, it will adorn the pre-dawn hours in the constellation Virgo, ascending toward Leo as the weeks advance. But by that time, it will be hurtling away from the Sun at over 150,000 miles per hour, becoming fainter each night as it retreats to the cosmic depths. For amateur stargazers hoping for a glimpse of this visitor from another star, the outlook is not promising. At its peak brightness, 3I Atlas will scarcely reach magnitude 11 or 12, visible solely through telescopes as a dim, hazy point among countless others. There will be no naked-eye spectacle, no brilliant tail stretching across the sky like Comet Hale-Bopp or Neowise. This visitor prefers to maintain a low profile. The orbital mechanics reveal another layer to the enigma. 3I Atlas is not just moving swiftly, it's moving incorrectly. Its hyperbolic orbit indicates an initial velocity of around 25 kilometers per second relative to the local standard of rest. This speed is sufficient not just to depart our solar system, but potentially to break free from the gravitational pull of our entire galactic vicinity. This is not some recently cast-off debris from a nearby star-forming region. This is something that has been journeying through the galaxy for a very, very long time. As spring transitions to summer in 2026, 3I Atlas will make another notable passage, this time near Jupiter in March. This distant meeting has already prompted proposals to alter the course of NASA's Juno spacecraft, which is currently orbiting the gas giant, to try for an intercept. It is a bold concept that would demand precise orbital mechanics and flawless timing, converting a mission intended to study Jupiter's interior into humanity's first close encounter with a confirmed interstellar visitor. But perhaps the most humbling part of this celestial itinerary is what it reveals about my cosmic perspective. Here I am, tracking an object with instruments valued at billions of dollars, coordinating observations across multiple space agencies, and gathering the most brilliant minds in planetary science. All this to study something that will spend less than 2 years in my vicinity before vanishing forever into the galactic darkness. The path of 3I Atlas through my solar system is not merely a trajectory. It is a timeline of opportunity and constraint, of windows opening and closing by the ancient principles of orbital mechanics. And every passing day brings me closer to my final opportunity to resolve the mystery of this wanderer from the stars. Part 3, First Looks. What Hubble Sees. When the Hubble Space Telescope first directed its steady gaze toward 3I Atlas on the 21st of July, 2025, the cosmos presented me with a paradox cloaked in starlight. The resulting image from Hubble's digital sensors was both recognizable and entirely strange, a teardrop-shaped cocoon of dust and gas glowing faintly against the unending blackness, yet exhibiting a geometry for which no textbook had prepared me. The technical specifications read like poetry, composed in the language of physics. The nucleus, the solid core of this interstellar wanderer, remained stubbornly unresolved, appearing as just a bright point source concealed within its own atmospheric veil. However, Hubble's remarkable optics enabled me and my colleagues to set an upper boundary on its dimensions, no larger than 3.5 miles across, which is about 5.6 kilometers in diameter. To put this into context, that is smaller than most terrestrial cities. Yet this diminutive fragment from another star system was producing a coma that extended for thousands of miles in all directions. But it is here that the familiar becomes peculiar. Hubble followed the comet against the backdrop of stars, maintaining 3I Atlas in the perfect center of its view. As a result, the stars themselves show up as bright lines across the image, crafting an ethereal setting that makes the comet seem as if it is journeying through a tunnel of light. It is a photographic method that turns scientific record-keeping into unintentional art, exposing the relative movement that distinguishes this visitor from everything else in my cosmic vicinity. The coma itself narrated a tale of thermodynamics unfolding on an interstellar scale. As 3I Atlas neared the Sun, crossing the 4 astronomical unit boundary where water ice actively sublimates, the nucleus started to shed material in a process that had likely been inactive for millions of years. The dust particles, freed from their icy framework, created a generally spherical cloud around the nucleus, but with a noticeable elongation pointing away from the Sun's direction. This was not arbitrary. This was physics at work. Solar radiation pressure and gravitational forces were shaping the coma into its signature teardrop form. Yet something about the tail seemed amiss. In most comets, the anti-solar tail, the stream of material pushed away from the Sun by radiation pressure, is conspicuous and easy to see. In 3I Atlas, this characteristic was surprisingly faint, almost concealed. Initial Hubble analyses hinted at its existence but could not definitively confirm it. The geometry appeared wrong, as if I were observing the tail from an angle that compressed it into near invisibility. This uncertainty would continue until late August, when the Gemini South Telescope in Chile took deep images that at last showed what Hubble had only suggested. There it was, a faint yet clear anti-solar tail stretching away from the Sun like a delicate thread in the cosmic breeze. The astronomer's telegram number, 17,363, made it official. 3I Atlas had the tail that theory required, but it was following its own rules of visibility. The rates of dust loss presented another piece of the puzzle. Hubble's data indicated that 3I Atlas was shedding material at a pace similar to comets from our solar system observed at comparable solar distances. This might seem reassuring, proof of normal, predictable activity, except for one vital point. This object had traversed interstellar space for eons, exposed to cosmic radiation that should have fundamentally changed its surface chemistry. Yet here it was, acting like a pristine comet on its inaugural journey through the inner solar system. The resolution of Hubble's imagery, among the best achievable from Earth orbit, revealed another layer to the enigma. While the telescope could constrain the nucleus's size and chart the coma's structure, it was unable to resolve any surface details or determine its rotational state. The nucleus remained a point source, its secret secured behind the glowing veil of its own atmospheric emissions. I was studying this visitor through the mist of its own creation, like attempting to inspect a lighthouse lamp while standing in its beam. Perhaps most compellingly, Hubble's observations hinted at internal structure within the coma itself. The dust's distribution was not perfectly uniform. There were slight variations in brightness and density that suggested active zones on the nucleus's surface. Somewhere beneath that covering of vapor and dust, specific areas were releasing material into space, forming the patterns Hubble detected. But without higher resolution or multiple viewing angles, those patterns remained as enigmatic as ancient hieroglyphs. The photometry uncovered another surprise. 3I Atlas was brighter than anticipated for an object of its estimated size, indicating either a larger nucleus than the size limit suggested, or a surface with exceptionally high reflectivity. Both scenarios raised questions about its composition and origin. Dark, carbon-rich materials would result in a faint object. Bright, icy surfaces would produce the luminosity Hubble saw, but the range of possibilities left too much room for speculation. As August advanced and 3I Atlas continued its approach to the Sun, Hubble's observations recorded the dynamic evolution of the coma. The dust cloud was expanding, growing as solar heat intensified. Yet the nucleus remained unresolved, a cosmic puzzle that revealed just enough to affirm its strangeness without clarifying its nature. The images would soon be supplemented by data from other instruments, each contributing pieces to a puzzle that seemed to grow more intricate with every observation. But Hubble had set the visual precedent. This was no common piece of interstellar debris. This was something that called for an explanation, something that challenged my understanding of what an interstellar visitor ought to look like. In the quiet darkness of space, 3I Atlas pursued its ancient voyage, now lit by my sun's light and examined by humanity's most advanced instruments. Yet, for all my technological skill, the visitor remained fundamentally unknowable, a mystery clad in starlight and enveloped in its own luminous breath. Part 4. The Chemistry Surprise. The cosmos has a knack for keeping us astronomers humble, and 3I Atlas was poised to teach a master class in cosmic modesty. When the James Webb Space Telescope, humanity's most powerful infrared eye, first examined the visitor's spectral signature on the 6th of August, 2025, the findings demolished every assumption I had formed from studying its forerunners. The figures told a story that was nonsensical, a carbon dioxide to water ratio of 8:1. To grasp how remarkable this measurement is, I must consider that most comets in my solar system display the opposite trend. Water is the dominant chemical by factors of 10 to 100. Even the most water-deficient comets seldom have carbon dioxide to water ratios greater than 2:1. Yet here was 3I Atlas displaying a chemical signature so pronounced it placed it in a class of its own. But Webb's discovery was merely the first act. Between the 8th and 12th of August, the SPHEREX mission, NASA's Wide-Field Infrared Surveyor, turned its focus to this interstellar anomaly and found something that defied all models of cometary behavior. The carbon dioxide emission was not limited to a small area around the nucleus. Instead, it reached outward for at least 348,000 kilometers, nearly 250,000 miles, forming the largest carbon dioxide coma ever recorded around any comet. I imagine the entire Earth-Moon system, then extend that distance by another 50%. That is the magnitude of 3I Atlas's carbon dioxide envelope, a spectral sphere of gas large enough to encompass multiple planetary orbits. The immense size of this emission area pointed to processes operating on scales that challenged my understanding of cometary physics. The spectroscopic data portrayed a picture of chemical extremes. While Webb identified strong carbon dioxide emission lines, the water signature was oddly subdued, so weak that some of my colleagues wondered if 3I Atlas contained any significant water ice at all. This was in sharp contrast to earlier findings from the Swift Observatory, which had spotted hydroxyl radicals that typically signal water photodissociation. Somewhere in the process of conversion from ice to gas to hydroxyl, the story of the water was being obscured. SPHEREX contributed another layer to the chemical story. Its wide-field spectral mapping detected absorption features at 1.5 and 2.1 micrometers, spectroscopic fingerprints that were consistent with water ice on the surface or in the near-surface layers. So the ice was present, locked in solid form, but something was inhibiting its efficient sublimation into the gas phase. The surface held secrets that the spectrum could only suggest. The difference from previous interstellar visitors was notable. Tubai I. Borisov, found in 2019, had shown elevated carbon monoxide, not carbon dioxide, relative to water. That chemical signature implied formation in a cold outer disk region where carbon monoxide ice could form. But carbon dioxide tells a different tale. It forms at moderate temperatures in areas where water would be liquid or vapor, but carbon dioxide could still freeze out of the gas. The implications sent ripples through theories of planetary formation. If 3I Atlas formed near a carbon dioxide snowline in another star system, it could represent material from a zone similar to the asteroid belt in my own solar system, an area too warm for water ice but cool enough for carbon dioxide to condense. Such regions might be common around other stars, but I had never before sampled material from one. The extensive carbon dioxide cloud brought up even more profound questions. How can a nucleus only a few kilometers wide generate and support an emission area larger than most planetary orbits? The physics required either an incredibly productive surface, far more active than anything I had seen in solar system comets, or a fundamentally different process for releasing gas into space. Some of my colleagues proposed that 3I Atlas might be breaking apart, releasing chunks rich in carbon dioxide that continue to sublimate as they drift away from the main core. Others suggested that the extended emission could be the result of solar-wind interactions with a pre-existing gas cloud, which would amplify the apparent size of the active zone. Both ideas pushed the limits of conventional comet science. The timing of these discoveries could not have been more dramatic. Just as 3I Atlas was entering the ideal viewing window before solar conjunction, its chemistry was proving to be unlike anything in my catalog of interstellar objects. I was witnessing a unique chemical laboratory in motion, fueled by my sun, but carrying the frozen history of an alien planetary system. Yet the dominance of carbon dioxide also carried a sobering implication. If this was characteristic of interstellar material, then my models of how planetary systems form and develop might be lacking critical components. The chemical diversity of 3I Atlas, combined with the contrasting signatures of 1I Oumuamua and 2I Borisov, suggested that the galaxy contains a population of ejected debris far more varied than my theories had anticipated. As August moved toward September and the observing window started to shrink, I found myself with data that was both unprecedented and inadequate. The chemistry of 3I Atlas was clearly exceptional, but whether it represented a new type of interstellar object or just an extreme case of known physics was still an open question. The universe, it seemed, was set on keeping me in suspense until the very last minute. Part 5. What we still don't know. 3 months following its discovery, with some of the world's most sophisticated instruments focused on 3I Atlas, I find myself in the strange situation of knowing too little about too much. Each observation has uncovered new aspects of this interstellar puzzle, yet the fundamental questions that are most important remain tantalizingly unresolved. The size of the nucleus perfectly illustrates my dilemma. Hubble's imaging limits the diameter to a range between 320 meters and 5.6 kilometers, a span so wide it covers everything from a large structure to a small city. This is not a failure of technology. It is the unavoidable result of studying an unresolved object concealed in its own glowing atmosphere. The nucleus could be a compact, bright sphere or a long, dark chunk spinning through space. Without direct resolution, I am essentially making an educated guess. The rotational state is equally enigmatic. Most small bodies in our solar system rotate with periods that can be measured in hours, and their changing cross-sections result in detectable variations in brightness as they spin. Yet 3I Atlas has demonstrated a frustratingly constant apparent brightness, exhibiting none of the periodic fluctuations that would indicate its spin rate or orientation. Either it is rotating very slowly, spinning nearly pole-on relative to Earth, or its surface features are remarkably consistent. Each scenario has different implications for its origin and structure. The question of water has transformed into something of a scientific saga. Initial observations by the Swift Observatory's ultraviolet and optical telescope identified hydroxyl radicals, usually a dependable sign of water vapor, being broken down by solar ultraviolet radiation. The presence of OH suggested significant water outgassing, which aligned with cometary expectations. However, SphereX's subsequent analysis found the water signal to be unexpectedly faint, establishing upper limits that conflicted with the Swift findings. Either the water is present but obscured by observational effects, or my understanding of hydroxyl production in cometary environments needs to be re-evaluated. The morphology of the tail adds another degree of ambiguity. The Gemini South detection of an anti-solar tail in late August finally affirmed what theory had predicted: material being pushed away from the Sun by radiation pressure. But why did it require months to clearly spot this feature? The tail's faintness compared to typical comets suggests either unusually large dust particles that are resistant to radiation pressure or a viewing geometry that compresses the tail's structure into near invisibility. Both explanations bring up questions about the fundamental nature of 3I Atlas. The patterns of activity present what is perhaps the most captivating unknown. The Hubble imagery reveals a sunward elongation of the coma, with material seemingly flowing toward our star instead of away from it. This counterintuitive arrangement initially baffled me and my colleagues until we considered that viewing angles can create optical illusions in three-dimensional gas flows. The apparent sunward movement might just be my perspective on a complex, three-dimensional outgassing pattern. Or it could signify something genuinely strange about how this visitor expels material. The mysteries of its composition go beyond the dominance of carbon dioxide. While Webb and Spherex have identified the primary gas species, they have only just begun to explore the trace chemistry. What about organic compounds? Sulfur-containing species? Noble gases? Each trace element could offer clues about its formation, temperature, radiation exposure, and the chemical conditions of its parent planetary system. But detecting these species demands observation time that is quickly diminishing. Perhaps most frustrating is my inability to observe 3I Atlas's behavior around perihelion, the very period when solar heating should induce the most significant changes in its activity and composition. The solar conjunction blackout ensures I will miss the culminating moment when this visitor passes closest to my star. I will only see the consequences, like showing up at a theater after the final curtain has fallen. The velocity of 3I Atlas exacerbates every observational difficulty. Ground-based telescopes must track at speeds that strain their pointing mechanisms to their maximum capacity. Space-based instruments are confronted with scheduling difficulties as the target moves swiftly across the sky. And the constantly increasing distance means that each week of delay leads to significantly poorer signal-to-noise ratios for spectroscopic observations. The kinematics present their own narrative of uncertainty. While its interstellar origin is established beyond any doubt, tracing 3I Atlas back to its stellar nursery demands precise trajectory knowledge, a knowledge limited by my brief observational window and the gravitational disturbances it has undergone during its transit through my solar system. The current most plausible estimate points to an origin in the galaxy's thick disk population among stars that formed when the universe was perhaps half its present age. But that is an educated guess based on incomplete information. Even the fundamental question of what propels 3I Atlas's activity is unresolved. Is it sublimating ices like a standard comet? Is it breaking apart under thermal strain? Could it be electrically charged, interacting with the solar wind in peculiar ways? The extensive carbon dioxide coma suggests activity on scales that simple sublimation models find difficult to explain. As I approach the solar conjunction deadline, the growing uncertainties foster a unique scientific tension. I know enough about 3I Atlas to see its extraordinary nature, but not enough to comprehend what makes it so. The December reappearance will present one last opportunity to solve the mystery or to confirm that some cosmic secrets are intended to stay concealed. The universe, it would appear, is especially fond of visitors who show up with more questions than answers. Part 6. What counts as interstellar? The cosmos does not provide passports, but if it did, 3I Atlas would have documentation from another star system. To comprehend what makes an object genuinely interstellar, I must delve into the mathematics of orbital mechanics, a language where eccentricity values and hyperbolic trajectories narrate stories of cosmic journeys that last for millions of years. In the specific language of celestial mechanics, any object having an orbital eccentricity exceeding 1 is not bound to our solar system. It is tracing what mathematicians term a hyperbolic trajectory, a path that extends to infinity instead of closing into an ellipse. 3I Atlas has an eccentricity of about 1.7, which means it is not just unbound, but is moving so quickly that even Jupiter's immense gravitational pull can hardly alter its course. But eccentricity alone does not provide the full picture. The truly defining measurement is known as V-infinity, the velocity an object would possess relative to the Sun if it were at an infinite distance, beyond the influence of solar gravity. For objects that originated in our solar system, this velocity is effectively zero. They are gravitationally tied and will eventually come back, even if their orbits take millennia to complete. 3I Atlas has a V-infinity of roughly 25 kilometers per second, confirming beyond any doubt that it came from elsewhere. To appreciate this speed, I consider that Earth orbits the Sun at approximately 30 kilometers per second. 3I Atlas is moving nearly as fast relative to the solar system as my entire planet travels around my star. That represents the momentum of a different world altogether, the kinetic signature of a formation environment where different physical laws dictated the interplay of gravity and motion. The process of discovery itself highlights just how uncommon these interstellar travelers are. The Atlas Survey System, an acronym for Asteroid Terrestrial Impact Last Alert System, is composed of 4 robotic telescopes engineered to scan the entire visible sky every 2 days in search of potentially hazardous asteroids. In almost a decade of service, after scanning millions of square degrees and cataloging hundreds of thousands of objects, Atlas has identified precisely 1 confirmed interstellar guest. The statistics are humbling. Interstellar objects are perhaps 1,000,000 times less common than typical near-Earth asteroids. This scarcity is not necessarily because interstellar space is vacant, quite the contrary. Theoretical models propose that every cubic light-year of my galactic vicinity should be filled with thousands of interstellar rocks, fragments cast out from planetary systems during their turbulent formation periods. The issue lies in detection. These objects are dim, swift, and follow paths that take them through our inner solar system for only short durations. By the time I spot them, they are often already speeding toward the exit. The technological revolution in wide-field surveys has finally provided me with the instruments to locate these cosmic wanderers. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, identified 1I Oumuamua in 2017. The Catalina Sky Survey found 2I Borisov in 2019. Now Atlas has given me 3I Atlas. Each discovery depended on automated systems capable of analyzing thousands of images each night, checking them against star catalogs, and highlighting the few moving objects that warrant human scrutiny. The confirmation procedure adheres to a strict protocol that would hold up in any court. An initial detection prompts rapid follow-up observations to determine orbital elements within days. Observatories around the world provide positional data that refine the trajectory. Orbital mechanics software computes the best fit orbit, assessing whether the movement is consistent with a solar system origin or necessitates an interstellar explanation. Only when multiple independent analyses confirm a hyperbolic motion and rule out all potential solar system parent bodies does an object receive an interstellar designation. The naming conventions reflect this meticulous verification process. The I designation for interstellar is given only after extensive review. 1I for Oumuamua, 2I for Borisov, 3I for Atlas. Each number signifies not just a discovery, but a verified sample from the vast population of debris that roams between the stars. Yet these 3 confirmed visitors suggest a much larger population awaiting discovery. The Rubin Observatory, currently being built in Chile, will commence operations in 2025 with a survey capacity that will overshadow all existing systems. Its wide-field camera will chart the entire southern sky every 3 nights, with a sensitivity that could detect interstellar objects years before they reach perihelion. Theoretical projections indicate Rubin could identify anywhere from 1 to 70 interstellar visitors annually, converting these infrequent cosmic events into routine scientific opportunities. The physics of an interstellar designation carries profound implications. These objects are time capsules from other star systems, preserving chemical and isotopic signatures from planetary formation environments I can never visit. Each visitor is a laboratory specimen delivered to my doorstep, bearing evidence of conditions around stars that might be hundreds of light-years away and billions of years younger than my Sun. The hyperbolic trajectories also mean I get only one opportunity to study each visitor. Unlike periodic comets that come back for repeated observations, interstellar objects are fundamentally single-use encounters. The data I collect during their brief transit through my observational sphere is the only information I will ever possess about these specific samples from the galactic debris field. As 3I Atlas continues its hyperbolic journey toward perihelion, its interstellar credentials are not in question. The mystery is not whether it originated from another star system. The orbital mechanics prove that definitively. The mystery is what kind of star system could create such a peculiar wanderer, and what its unusual chemistry reveals about planetary formation in environments completely different from my own. Part 7. 3 visitors, 3 personalities. The cosmos possesses a unique sense of humor, and this is nowhere more evident than in the collection of interstellar visitors that have entered my solar system. In less than 10 years, I have welcomed 3 confirmed guests from other star systems. Each one arrived with a character so individual that they seem crafted to challenge every assumption I make about the space between stars. First was Oumuamua in 2017, the cosmic parallel to a stoic stranger entering a small-town saloon. It had no visible coma, no tail, and no outgassing that my telescopes could detect. It was just a spinning, cigar-shaped object that reflected sunlight like burnished metal. Its conduct was almost aggressively ordinary until it started to accelerate away from the sun for no apparent reason. The acceleration was minor but detectable, about 1/10,000th of Earth's gravity. Yet it broke every rule of how inert rocks should act in space. The scientific community engaged in a heated debate. Some suggested unusual mechanisms: hydrogen outgassing from subsurface ice, radiation pressure on an exceptionally reflective surface, or even more speculative concepts involving solar sails or electromagnetic forces. The acceleration was real. Multiple observatories verified it, but its origin remained infuriatingly unknown. 1I Oumuamua had transformed gravitational physics into a detective story, leaving behind more questions than answers as it disappeared into interstellar space. Next was 2I Borisov in 2019, which arrived like a familiar acquaintance bringing strange presents. Here, at last, was an interstellar visitor that acted like a proper comet, with a bright coma, a prominent tail, and a steady release of water vapor and dust. All the characteristics astronomers like me anticipated from a piece of primordial ice. But Borisov had its own chemical surprise, a high concentration of carbon monoxide that greatly surpassed anything seen in comets from our solar system. Its carbon monoxide to water ratio suggested it formed in a region colder than the far reaches of my own system, perhaps around a star with a more extensive disk of icy material. Now 3I Atlas has made its entrance as the third act in this interstellar play, and its chemical makeup appears to be a deliberate effort to disrupt the patterns I thought were emerging. Where Oumuamua displayed no gas and Borisov had excess carbon monoxide, 3I Atlas is dominated by carbon dioxide. The sequence of no detectable outgassing to carbon monoxide surplus to carbon dioxide dominance suggests a sampling of formation environments so varied that each visitor might as well have come from a separate universe. The contrasts in their morphology are just as remarkable. Oumuamua's elongated, tumbling shape suggested either a natural fragment or something more geometric in origin. Its 10-to-1 length-to-width ratio was extreme, even for an asteroid, leading to speculation about whether it might be artificially constructed. Borisov, on the other hand, looked entirely conventional, a roughly spherical nucleus surrounded by a symmetrical coma and featuring a textbook antisolar tail. 3I Atlas occupies a middle ground in the most perplexing way imaginable. Its coma is compact and generally spherical, indicating a solid nucleus rather than a fragmented body. But the faint tail that finally appeared in late August images is oddly subdued compared to Borisov's prominent plume. The geometry implies controlled, localized outgassing rather than the explosive activity common in comets approaching perihelion. The size estimates for each visitor tell their own story of variety. Oumuamua was about 400 meters long, but only 40 meters wide, a cosmic needle. Borisov's nucleus was estimated to be about half a kilometer across, standard for a medium-sized comet. 3I Atlas falls somewhere between these two, with an upper size limit of 5.6 kilometers, but potentially much smaller. Each visitor represents a different scale of debris from the interstellar population. Perhaps most compellingly, the three visitors arrived with completely different apparent brightnesses and discovery conditions. Oumuamua was identified as it was already speeding away from the Sun, found almost by chance during routine asteroid searches. Borisov was detected while still approaching the outer solar system, which allowed for months of advance planning. 3I Atlas was captured at the perfect moment, far enough away to plan observations, yet close enough to begin detailed analysis immediately. The chemical signatures suggest formation in three distinct environments. Oumuamua's absence of detectable outgassing might indicate processing by interstellar radiation, complete devolatilization, or formation in an exceptionally dry part of its home system. Borisov's high carbon monoxide content points to an origin in the cold outer regions of a protoplanetary disk. 3I Atlas's dominance of carbon dioxide suggests moderate formation temperatures, perhaps in an area where water was a vapor but carbon dioxide could still condense. The behavioral differences extend beyond chemistry to fundamental physics. Oumuamua's unexplained acceleration hinted at forces other than simple gravitational pull, whether from outgassing too faint to detect, radiation pressure on an unusual surface, or mechanisms I have yet to identify. Borisov adhered to predictable comet physics, its trajectory perfectly matching gravitational models with no unaccounted-for deviations. 3I Atlas so far seems to be gravitationally well-behaved, but its extensive carbon dioxide coma challenges my understanding of how small nuclei can produce such enormous gas clouds. The effects of observational bias are significant. What I observe is entirely contingent on geometry, timing, and the sensitivity thresholds of my instruments. Oumuamua's lack of visible activity might have appeared very different if I had caught it during an active period. Borisov's classic appearance might have seemed unusual if I had viewed it from a different angle. 3I Atlas's faint tail could be far more dramatic when seen from Mars's perspective during the October flyby. Yet, these three personalities, the mysterious accelerator, the carbon monoxide classic comet, and the carbon dioxide enigma, already hint at the vast diversity awaiting discovery. If the first three interstellar visitors are this different from one another, what will the next dozen reveal? Each visitor is like a core sample from a different planet-forming environment, carrying chemical fingerprints that record the thermal history and composition of alien worlds I will never see. The progression from Oumuamua to Borisov to 3I Atlas feels like the universe is systematically refuting every assumption I have about what interstellar debris should look like. Just when I thought I understood the category, another visitor arrives to rewrite the rules completely. As 3I Atlas nears its encounter with solar conjunction, I am left to wonder if its strange character is just the tip of an even more bizarre iceberg, or if I am simply discovering that the space between the stars is far more chemically diverse than I ever imagined. Part 8. The Dynamics Puzzles. The cosmos has a method of concealing its most vital secrets within the slightest departures from the expected, and this is nowhere more clear than in the subtle interplay of forces that dictates how interstellar visitors travel through my solar system. The story of 3I Atlas is, at its heart, a story of physics in action, of minute accelerations that could unveil profound truths about the nature of matter in the space between stars. 1I Oumuamua set the standard for interstellar mystery when it started to accelerate away from the Sun in a way that contradicted gravitational models. The effect was minuscule, roughly 10 micrometers per second squared, about 1/10,000th of Earth's surface gravity, but it was consistent and measurable over weeks of observation. Multiple observatories confirmed the acceleration's reality, turning what should have been a simple gravitational issue into a puzzle that still inspires research papers years later. The acceleration was not random. It followed a distinct pattern that suggested outgassing from the sun-facing side. But this is where Oumuamua became truly baffling. No telescope could spot the gas or dust that should be associated with such outgassing. The object was accelerating like a comet, but looked like an asteroid, creating a paradox that led astronomers like me to consider increasingly unusual explanations. Some of my colleagues suggested that Oumuamua might be releasing hydrogen, a gas so rarefied and hard to detect that it could account for the acceleration without forming a visible coma. Others proposed that radiation pressure on an exceptionally reflective surface could explain the observed movement. The most speculative theories involved artificial origins, although these were far from mainstream scientific agreement. 3I Atlas, in contrast, has not yet shown a similar acceleration anomaly. Its trajectory aligns with gravitational predictions within observational error, following the smooth hyperbolic curve that Newton's laws require. But this apparent normalcy could be deceptive. The non-gravitational forces that influenced Oumuamua only became clear during prolonged observation as the object moved away from the Sun's gravity. 3I Atlas is still nearing perihelion, and the most revealing data may be gathered during and after its closest pass to the Sun. The chemistry of 3I Atlas suggests that if non-gravitational forces do appear, they might follow a very different pattern than Oumuamua's hydrogen outgassing theory. Carbon dioxide sublimation releases much heavier molecules than hydrogen, which creates a momentum transfer that is easier to detect but is governed by different physics. If 3I Atlas begins to show a measurable acceleration, it could provide the key to understanding whether Oumuamua's behavior was a one-off or a common characteristic of interstellar visitors. The viewing geometry introduces layers of intricacy to any dynamical assessment. Anti-solar tails can seem compressed or even invisible depending on my line of sight relative to the comet's movement. The sun-facing coma elongation that Hubble observed in 3I Atlas initially confused observers like me, who anticipated that material would flow away from the Sun rather than toward it. But three-dimensional gas dynamics can create optical illusions where material moving in complex patterns appears to flow in counterintuitive directions when seen on the two-dimensional plane of the sky. The extended carbon dioxide coma constitutes its own dynamical enigma. How does a nucleus only a few kilometers wide maintain an active emission region that stretches for hundreds of thousands of kilometers? The physics demands either an extraordinarily productive surface, perhaps 100 times more active per unit area than typical solar system comets, or a mechanism that spreads gas-producing material over a much larger volume than the nucleus itself. One possibility is that 3I Atlas is actually a loosely bound collection of smaller fragments, each one outgassing on its own to form the extended emission area. But if this were true, I would expect to see signs of fragmentation in the images, such as multiple bright spots or elongated shapes that would indicate the presence of separate pieces. So far, Hubble's high-resolution images show no such features. Another explanation involves the interaction between outgassing and the solar wind. As carbon dioxide molecules leave the nucleus, they can be ionized by solar ultraviolet radiation, creating a population of charged particles that interacts with the solar magnetic field. These electromagnetic forces could accelerate the gas to much higher speeds than simple thermal expansion, potentially explaining the vast size of the carbon dioxide cloud. The rotational state of 3I Atlas is still unknown, but it could hold important clues about dynamical processes. Most small bodies spin chaotically due to outgassing torques, jets of gas that act like tiny rocket engines, gradually altering the object's spin. If 3I Atlas is outgassing as actively as its extensive coma suggests, it should be experiencing significant torques that would appear as brightness fluctuations in long-term photometry. Yet the photometric record shows remarkable stability, with none of the periodic brightness changes that would signal a tumbling motion. This could mean the object is spinning very slowly, is viewed nearly pole-on so that its rotation does not change its apparent cross-section, or has a surface so uniform that its rotation produces no detectable brightness variations. Each possibility has different implications for the object's structure and origin. The TESS observations, data from the Transiting Exoplanet Survey satellite, have suggested possible activity even at the great distances where 3I Atlas was initially spotted. If confirmed, this would imply that the visitor was already active when it was farther from the Sun than Jupiter, pointing to either an exceptionally volatile composition or a triggering mechanism other than simple solar heating. As 3I Atlas nears perihelion, the dynamical questions will only grow more intense. Will it exhibit the mysterious acceleration that characterized Oumuamua? Will its coma's morphology reveal the jet structures that would explain its extensive gas cloud? The answers could reshape my understanding of how interstellar matter behaves when it encounters a star system very different from its place of origin. The physics is unfolding in real time, written in the language of orbital mechanics and spectral signatures. I am witnessing dynamics that started in another star system millions of years ago, finally reaching their peak in the warm embrace of my Sun's gravity. Well, Part 9, the Global Watch. Who's observing what when? The astronomical field has made 3I Atlas the most intensely scrutinized interstellar guest in history, organizing a worldwide observation effort that unfolds like a scientific symphony performed across multiple continents and orbital platforms. Every major space agency and ground-based observatory has participated in what is effectively humanity's most coordinated attempt to understand a single small object moving through my cosmic vicinity. The NASA Science Mission Directorate set up the coordination structure, arranging a multi-mission strategy that utilizes every available resource. The Hubble Space Telescope offers the highest resolution imagery, monitoring changes in the coma's morphology and establishing limits on the nucleus's size that no ground-based instrument can rival. The James Webb Space Telescope provides infrared spectroscopy with a sensitivity that can identify trace gases at concentrations as low as parts per million. The Swift Observatory tracks ultraviolet emissions that show the photochemical reactions breaking apart molecules in the coma. The SphereX mission has become an unforeseen star in this observation campaign. Initially intended to map the infrared sky for cosmological research, its wide-field capability was perfectly suited for tracking the immense carbon dioxide cloud that envelops 3I Atlas. The combined effect of Webb's high-resolution spectroscopy and SphereX's expansive mapping has yielded a comprehensive view of both chemical makeup and spatial extent, data that no single instrument could have delivered on its own. Ground-based observatories across the globe have synchronized their activities through the International Astronomical Union's rapid response networks. The Gemini North Telescope in Hawaii was responsible for capturing the first pictures that showed the compact coma of 3I Atlas. Its counterpart, Gemini South in Chile, delivered the deep imaging in late August, which ultimately verified the faint antisolar tail. The Palomar Observatory's next-generation Palomar survey is providing continuous photometry and astrometry, which helps in monitoring changes in brightness and improving the orbital calculation with every new observation. However, the schedule of observations is constrained by a definite astronomical reality: solar conjunction. As 3I Atlas makes its closest approach to the Sun on October 29, 2025, the position of Earth in relation to the Sun results in a viewing situation that is both aggravating and beautiful. Precisely when this interstellar traveler enters its most dynamic period, it will vanish behind the glare of our star, rendered invisible to all Earth-based telescopes for almost 2 months. This blackout interval is one of the most frustrating coincidences in astronomy. The moment when solar radiation should incite 3I Atlas to its peak activity, when the temperature of its nucleus reaches its maximum and outgassing rates hit their zenith, will be entirely beyond our planet's view. We are set to miss the climax of this cosmic event, able to examine only its beginning and conclusion. Its reappearance in early December will signal the start of the final phase. 3I Atlas will become visible in the sky before dawn, located in the Virgo constellation, before ascending toward Leo over the subsequent weeks. By that time, it will be speeding away from the Sun at speeds greater than 150,000 miles per hour, dimming with each passing night as it journeys back to the interstellar void. The observations after perihelion will be a contest against both time and distance, as the signal's intensity diminishes exponentially with the visitor's retreat. Still, this difficult schedule has spurred innovative approaches that highlight the cleverness of contemporary space exploration. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment, HiRISE, offers a special chance to view 3I Atlas from an extraterrestrial viewpoint. On October 3, 2025, the object will pass within 29 million kilometers of Mars, which could enable orbiting instruments to take pictures during the time Earth's observation is impossible. The image quality would not match the sharpness of Hubble, yet it would furnish essential data during the time when telescopes on Earth are unable to see. A number of spacecraft that are currently journeying through the outer solar system have been pinpointed as possible contributors to this observation effort. NASA's Psyche mission, which is heading to a metallic asteroid, is set to pass within approximately 0.3 astronomical units of 3I Atlas on September 4, 2025. The European Space Agency's Jewish spacecraft en route to Jupiter's moons might try to conduct long-distance observations as it approaches on November 4th. The OSIRIS-APEX mission has also been looked at for potential imaging opportunities starting in late 2025. Although the geometric difficulties are still considerable, the collaborative effort goes beyond conventional astronomical instruments. Radio telescopes across the globe are searching for any electromagnetic signals that could suggest electrical phenomena or strange interactions with the solar wind. Planetary radar facilities are trying to reflect signals from the nucleus in the hope of determining its size and rotation speed from the echo delays. Even networks of amateur astronomers have been called upon to provide photometric data that can bridge the gaps in the coverage by professional astronomers. This international collaboration has led to an observation schedule that brings to mind military-style logistics. Committees that allocate time at leading observatories have approved emergency viewing periods, thereby interrupting well-laid-out research plans to seize this cosmic chance. Agreements for sharing data make sure that spectroscopic findings from one observatory can be promptly compared with images from another, fostering scientific collaborations that enhance the worth of every single observation. The European Space Agency's Planetary Defense Office has organized tracking initiatives that are motivated by more than just scientific interest. Even though 3I Atlas is not a danger to Earth, the methods being created to track its path and forecast its actions will be extremely useful in future situations involving planetary defense. Each determination of its position and speed adds to the orbital models that could one day be used to shield our world from visitors that are not so harmless. As the time for observation shortens before the solar conjunction, the level of worldwide surveillance has intensified greatly. Telescope time that usually demands years of competitive applications is now being assigned on a weekly basis. The analysis of data, which typically takes several months, is being condensed into a matter of days. The community of astronomers has effectively labeled 3I Atlas a cosmic emergency, not due to any threat it presents, but because it is a chance that will not occur again. Its reappearance in December will put every element of this worldwide cooperative effort to the test. Will we be able to sustain the same degree of intense observation when the object is dimmer and further away? Will the chemical composition after perihelion unveil the mysteries that the observations before perihelion could only allude to? The coming few months will show whether this unique observational effort will produce the groundbreaking discoveries that could change our knowledge of interstellar space. Part 10. Could we fly to it? The romantic idea of pursuing an interstellar traveler with a rapidly deployed spacecraft is quickly dismissed by the strict laws of orbital mechanics and the harsh truths of rocket technology. Nevertheless, the sheer unfeasibility of reaching 3I Atlas has sparked some of the most imaginative mission design concepts in recent times. These concepts stretch the limits of what is theoretically achievable with our current technology. The main issue is the combination of time and speed. 3I Atlas was found when it was already moving at a speed of over 200,000 kilometers per hour toward the inner solar system. Any mission to intercept it would need to match not only this incredible speed, but also its exact vector, which includes the direction and orientation of that speed in three-dimensional space. The amount of energy needed for such a path places it squarely in the category of science fiction, given our present propulsion capabilities. An interceptor mission sent from Earth would need a change in velocity, or delta phi, that is 10 or more times greater than what our most powerful rockets can achieve. Even if we could somehow produce the required thrust, the journey to an interception point would last for years, by which time 3I Atlas would be far gone, vanishing into the interstellar medium beyond any practical means of pursuit. But impossibility has never deterred aerospace engineers from dreaming. Several research teams have looked into what could be done using spacecraft that are already traveling through the solar system. The Psyche mission, which is on its way to examine a metallic asteroid, will come within 0.3 astronomical units of 3I Atlas on September 4, 2025. Although Psyche was not built for encounters with comets, its set of instruments contains cameras and spectrometers that could, in theory, collect useful data during its flyby. The Jewish mission, which is the European Space Agency's Jupiter Icy Moons Explorer, offers another chance for unexpected scientific discovery. The path of Jewish will bring it close enough for observation of 3I Atlas on November 4, 2025, during the time when telescopes on Earth are blocked by the solar conjunction. The advanced imaging and spectroscopy instruments on the spacecraft could supply vital data during this period of no observation. However, the geometry of the encounter and the operational limitations are still major obstacles. Perhaps the boldest idea involves NASA's Juno spacecraft, which is currently in orbit around Jupiter and studying the gas giant's internal composition. A team of researchers led by astronomers at the Harvard-Smithsonian Center for Astrophysics has figured out that a precisely timed change in its path could send Juno toward an encounter with 3 Atlas in March 2026. This plan would use the immense gravitational pull of Jupiter as a cosmic slingshot, increasing its velocity through a maneuver that takes advantage of the spacecraft's closeness to the giant planet. The Juno intercept proposal sounds like a space mission fantasy brought to life. The spacecraft would have to perform a perfectly timed engine burn while deep within Jupiter's gravitational field, using the planet's orbital energy to accelerate onto an intercept path. The timing would have to be exact. If the window is missed by even a few hours, the encounter would be impossible. If the maneuver is carried out flawlessly, Juno could become the first human-made probe to perform a close flyby of an interstellar visitor. But ideas like this are still just in the analysis phase, hindered by practical issues that go well beyond orbital mechanics. Juno's current mission is set to conclude in 2025, and any change to its trajectory would need approval from NASA headquarters, along with detailed mission planning and probably oversight from Congress. The aging systems of the spacecraft and its limited fuel supply present further difficulties to an already demanding proposal. The encounter with Mars on October 3, 2025, provides what is likely the most feasible chance for close-up observations. As 3I Atlas passes within 29 million kilometers of the red planet, the high-rise camera on the Mars Reconnaissance Orbiter might be able to take images with a resolution of about 30 kilometers per pixel. While this would not be as clear as Hubble's images, it would offer a special viewpoint during the critical time when observations from Earth are not possible. The OSIRIS-APEX mission, which was originally intended to study the asteroid Apophis, has been noted in several scholarly articles as a potential source for observations of 3I Atlas starting in late 2025. The spacecraft's array of instruments, designed for studying asteroids at close range, could yield unparalleled information about the surface characteristics and makeup of an interstellar visitor. However, the mission's schedule and trajectory limitations make such observations very uncertain. Looking ahead, the European Space Agency's Comet Interceptor mission is humanity's greatest hope for a mission specifically designed to meet an interstellar visitor. Set to launch in 2029, Comet Interceptor is conceived as a quick-response mission that can change its course toward targets of opportunity, including newly found interstellar objects. The spacecraft will remain in a gravitationally stable orbit, prepared to head toward whichever cosmic traveler arrives next. The academic writing on missions to intercept interstellar objects has grown significantly since the discovery of Oumuamua, with articles looking into everything from solar sails and fusion rockets to gravitational assist paths that use multiple planetary encounters. These studies act as evaluations of feasibility for future chances, setting out the technological and logistical needs for missions that are not yet real but could be one day. The energy needed for interstellar intercepts shows just how different these visitors are from regular targets in the solar system. While a mission to Mars needs a delta phi of about 6 kilometers per second and a flyby of Jupiter requires around 12 kilometers per second, intercepting an object like 3I Atlas would necessitate delta V values of nearly 50 kilometers per second or even more. This is beyond the reach of chemical rockets and would require either nuclear propulsion, solar sails, or propulsion methods that are still only theoretical. Yet the scientific rewards from a successful interception would be revolutionary. Close-up measurements of an interstellar visitor could disclose isotopic ratios that tell us about the stellar environment where it was formed, surface compositions that hold the chemical secrets of alien planetary disks, and structural features that show how small bodies endure the trip between star systems. Data like this would be more valuable than decades of observations from the ground, providing solid proof for theories about how planets form in environments that are completely different from ours. The sad irony is that every interstellar visitor is like a lab sample brought to our doorstep, but it moves too quickly for us to collect it properly. We are like scientists watching precious samples go by our lab window, so close yet impossible to catch with the technology we have now. As 3I Atlas continues its hyperbolic path toward its closest point to the Sun, the studies on interception serve as both frustrating reminders of our current limits and inspiring plans for what could be possible in the future. We may not be able to chase this visitor, but we are figuring out how to be prepared for the next one. Part 11. Why carbon dioxide? Natural explanations on the table. The cosmic composition of 3I Atlas seems like a formula from an alien recipe book, with carbon dioxide being the main ingredient in amounts that defy all the models we have created for how comets are supposed to act. Yet, before we explore more unusual theories, the principles of physics present several natural ways that could lead to such a distinct chemical profile. Each of these ways tells us something important about the environment where this visitor originated. The hypothesis of a carbon dioxide snowline offers what might be the most refined explanation for the strange chemistry of 3I Atlas. In any protoplanetary disk, various volatile substances condense at different distances from the central star, forming chemical zones as clearly defined as climate zones on Earth. While water ice is prevalent in the cold outer areas, carbon dioxide has its own freezing point at middle temperatures. An object that forms just inside the water snowline but outside the carbon dioxide snowline would gather a large amount of carbon dioxide ice while having relatively little water. This situation suggests that 3I Atlas was formed in an area similar to our asteroid belt. It was warm enough for water to be a vapor, but cold enough for carbon dioxide to freeze out of the gas. Such a setting would result in the exact chemical makeup we are seeing: plenty of carbon dioxide ice with only a small amount of water contamination. The area of formation would be a cosmic sweet spot, where thermodynamics favor carbon-containing volatiles over compounds of hydrogen and oxygen. But stellar environments differ greatly from one system to another, and the prevalence of carbon dioxide might indicate more unusual formation conditions. Stars with varying masses and brightnesses produce different temperature patterns in the disks around them. A star with low mass might shift the carbon dioxide snowline much closer to itself, enlarging the area where carbon dioxide ice is more common than water. On the other hand, a particularly bright star could create temperature gradients that encourage the formation of carbon dioxide through completely different chemical processes. Radiation processing is another persuasive explanation for the peculiar chemistry of 3I Atlas. Over its millions of years of travel through interstellar space, this visitor has been subjected to cosmic radiation at levels that would be fatal to any life on Earth. High-energy particles can break molecular bonds, change chemical structures, and even form entirely new compounds through radiolysis, a type of radiation-driven chemistry that acts like a cosmic laboratory conducting experiments at the molecular level. This kind of processing could account for both the dominance of carbon dioxide and the seeming lack of water. Cosmic rays might selectively break down water ice while leaving carbon dioxide largely unaffected. Alternatively, they might transform simple organic compounds into carbon dioxide through intricate reaction pathways. The reddish hue that Spherex observed in the spectrum of 3I Atlas is in line with radiation processing, indicating that its surface has indeed been chemically changed during its journey through interstellar space. The hypothesis of an insulating crust tackles one of the most perplexing aspects of the behavior of 3I Atlas. Why does it exhibit such strong carbon dioxide emissions while signs of water remain persistently faint? Laboratory experiments with similar materials show that mantles rich in organic compounds can develop on icy surfaces, forming insulating layers that selectively hinder the sublimation of volatiles. If 3I Atlas formed such a crust during its interstellar travels, water ice might be plentiful beneath the surface but kept from turning into gas by the material on top. Carbon dioxide, being more volatile than water at the same temperature, could escape through fractures or thin areas in this insulating layer, leading to the observed emission pattern. This would clarify why Webb detects a large amount of carbon dioxide gas, while FERC finds evidence of water ice in its solid form. The water is present, but it is confined beneath a surface layer that only allows carbon dioxide to get out. The hypothesis of icy fragments, put forward by scientists studying the large gas cloud, proposes a completely different process. Instead of being a single solid body, 3I Atlas could be an assembly of ice chunks rich in carbon dioxide, held together by weak gravitational and cohesive forces. As the heat from the sun increases, these pieces could break apart and sublimate on their own, forming the vast carbon dioxide coma through widespread outgassing over a much larger area than a single nucleus could create. This model of fragmentation would explain several confusing observations at once: the extensive gas cloud, the consistent brightness despite what seems to be high activity, and the subtle shape of the tail that suggests the production of large-grained dust. If 3I Atlas is basically a flying collection of carbon dioxide ice gravel, its actions would indeed be different from anything in our records of comets in the solar system. Temperature dependence offers yet another clue to this puzzle. At the current distance of 3I Atlas from the Sun, which is between about 2.5 and 3.5 astronomical units, the sublimation of water ice is not very efficient. While carbon dioxide is still highly volatile, the laws of thermodynamics naturally favor the outgassing of carbon dioxide over the production of water vapor. This could potentially explain the observed emission ratios without needing to resort to unusual formation environments or strange surface phenomena. As 3I Atlas continues to get warmer on its way to perihelion, this dependence on temperature provides a prediction that can be tested. If the dominance of carbon dioxide is simply due to thermodynamic effects, then observations after perihelion should reveal an increase in water emission as the temperature of the nucleus peaks and then starts to fall. The ratio of carbon dioxide to water should change in predictable ways that align with laboratory measurements of ice sublimation rates at various temperatures. The effects of grain size in the coma and tail give more insights into the composition of 3I Atlas. The faint anti-solar tail that appeared in late August points to either exceptionally large dust particles that can withstand radiation pressure or a special grain composition that alters how the material reacts to the forces of the solar wind. Laboratory studies on the sublimation of carbon dioxide ice indicate that it can create dust aggregates with different characteristics than those from water ice sublimation, which might explain the unusual shape of the tail. Each natural explanation for the chemistry of 3I Atlas provides a glimpse into the physics of planet formation in environments that we can never observe directly. Whether it was formed near a carbon dioxide snowline altered by interstellar radiation or as a group of fragments with a unique volatile composition, this visitor holds information about the conditions in stellar disks that broadens our knowledge of how planetary systems are formed. The natural possibilities are many, testable, and based on well-established physics. Yet the sheer number of them creates its own puzzle. With so many believable explanations at hand, how do we figure out which one, or which combination of them, truly represents the reality of this specific wanderer from the stars? Part 12. Where could it have come from? Trying to find the stellar origin of 3I Atlas is like trying to solve a murder case where the scene of the crime is light years away, and the clues are hidden in orbital mechanics that span across galactic history. However, concealed within the visitor's path are kinematic clues that suggest a certain group of stars, and therefore a particular period in the history of our galaxy's formation. The thick disk hypothesis has become the most likely explanation for the origin of 3I Atlas. Our Milky Way galaxy is made up of several separate populations of stars. The thin disk, where our Sun is located, has relatively young stars with a high content of heavy elements. The thick disk is inhabited by older stars that were formed when the galaxy was perhaps half its current age. And the ancient stellar halo contains the galaxy's most ancient and metal-poor stars. Each population moves through space with unique speeds and orbital paths that are a result of the gravitational environment where they were created. The velocity vector of 3I Atlas, which is its speed and direction in relation to the local standard of rest, points to its membership in the thick disk population. These stars were formed about 8 to 12 billion years ago, during what astronomers call the epoch of cosmic noon, a time when the rates of star formation across the universe were at their highest and the production of heavy elements was quickly enriching the interstellar medium. If 3I Atlas came from this stellar environment, it is made of material that has been traveling through the galaxy since before the Earth even formed. The origin from the thick disk has significant consequences for our understanding of planet formation in the early universe. The stars in this population were created from gas clouds that had fewer heavy elements than the environment where our Sun was born. This lower metallicity would have influenced the composition of any protoplanetary disks, possibly favoring carbon-bearing volatiles over species rich in oxygen, which could explain the unusual chemistry of 3I Atlas. But the story of its origin goes beyond simple star demographics to include the violent events that throw material out of planetary systems in the first place. Gravitational interactions with large planets can fling smaller bodies onto hyperbolic paths, sending them into interstellar space at speeds that are determined by the specific details of the encounter. Close flybys of stars can also disrupt planetary systems, tearing away material from the outer disk that then becomes the source for the population of interstellar debris. The mechanisms of ejection lead to a natural selection process in the interstellar medium. Only objects of certain sizes, compositions, and structural strengths can withstand the violent ejection and the subsequent millions of years of travel through interstellar space. 3I Atlas is a survivor of this cosmic filtering process, carrying chemical and physical traits that reveal both its formation environment and its history of survival. Population studies based on the 3 confirmed interstellar visitors show a sampling bias that makes any effort to deduce their origins more complex. We have found one object with no visible outgassing, one with an excess of carbon monoxide, and one with a dominance of carbon dioxide. This could be a true representation of the diversity of interstellar debris, or it might just be a reflection of the specific detection biases of our current survey systems. Objects with different size distributions, activity patterns, or approach paths might be invisible to our telescopes. The galactic context introduces another level of uncertainty to the origin stories. 3I Atlas has been journeying through space for millions of years, and during that time it has been affected by gravitational pulls from every star system it has passed. These encounters have slowly changed its path, wiping out the kinematic clues that would allow for a precise backtracking to its point of origin. We can identify the general population of stars it likely came from, but finding the exact star system may be impossible with the data we currently have. The chemical clues offer more definite restrictions on the environment of its formation. The prevalence of carbon dioxide necessitates temperatures and pressures that are only found in specific areas around forming stars. If 3I Atlas condensed from the gas phase in a protoplanetary disk, the thermodynamic conditions must have been more favorable to carbon dioxide than to water. This suggests either an unusual chemistry in the disk or formation at a particular orbital distance where these conditions naturally occur. Isotopic ratios could be the definitive proof of the origin of 3I Atlas. However, measuring isotopes in such a faint and distant object is at the very edge of what current spectroscopic methods can do. Different stellar environments create different isotopic signatures in their planets and debris, acting as chemical fingerprints that could identify not just the type of star system where 3I Atlas was formed, but possibly the specific stellar mass, age, and metallicity of its parent star. The Rubin Observatory's Legacy Survey of Space and Time, which will start its operations in the next few years, is set to change the study of origins from isolated case studies to a statistical science. It will have the ability to detect dozens of interstellar visitors each year. Rubin will create a sample large enough to show population trends and chemical patterns that single objects like 3I Atlas can only suggest. Early reports in some media outlets about an extragalactic origin for 3I Atlas seem to be based on unsupported speculation rather than scientific agreement. The kinematic evidence strongly suggests an origin within the Milky Way, most probably from the thick disk population. While the galaxy is immeasurably vast, it is not limitless, and the laws of orbital mechanics put clear limits on how far 3I Atlas could have traveled while keeping its observed path. The timing of the arrival of 3I Atlas in our solar system could be just a coincidence, or it might indicate deeper patterns in galactic dynamics that we have yet to understand. If the origin from the thick disk is correct, then 3I Atlas is material that was ejected from a planetary system billions of years ago, wandering through the galaxy during cosmic dark ages. It has survived supernovae and events of stellar evolution that have reshaped the galactic environment multiple times over. As we examine the chemistry and dynamics of this visitor, we are essentially performing archaeology on a galactic scale, deducing the characteristics of ancient planet-forming environments from the debris they left behind. 3I Atlas is a time capsule, but one that has been drifting through space for so long that its contents have been changed by processes we are only just starting to comprehend. The observations in December, when 3I Atlas comes out of solar conjunction, will provide essential tests for the hypotheses about its origin. If the chemistry after perihelion shows a predictable change based on thermodynamic models, it will back up formation scenarios that rely on conventional ice physics. If the chemistry stays stubbornly unusual, it might point to formation processes or later processing that go beyond our current theoretical understanding. Part 13, the A.V. Loeb chapter, Open-Minded and Controversial. In the world of modern astronomy, there are few individuals who provoke more heated discussion than Avi Loeb, the astrophysicist from Harvard whose readiness to consider unconventional ideas has made him both a target for criticism and a champion for scientific curiosity. His examination of 3I Atlas is a perfect example of this complex reputation, thorough in its observational basis, yet daring to the point of being provocative in its theoretical suggestions. Loeb's involvement with 3I Atlas started almost as soon as it was discovered, taking the form of a series of in-depth essays that followed the visitor's changing observational signs with the accuracy of a detective on a case. His analysis on August 27th was especially insightful, as he claimed to have spotted the faint anti-solar tail that standard observations had not seen. Within a matter of days, the astronomer's telegram number 17,363 confirmed exactly what Loeb had foreseen. The subtle tail feature was indeed there, noticeable to those who were willing to analyze their data to the very edge of what could be detected. But Loeb's understanding of 3I Atlas goes much further than just confirming the existence of typical cometary features. His estimations of its size, based on assumptions about its brightness and models of light scattering, suggest a nucleus that could be tens of kilometers wide, which is significantly larger than Hubble's upper limit of 5.6 kilometers. This difference is not just a matter of academic debate. It points to fundamentally different physical principles that control how this object interacts with sunlight. Either Loeb's brightness models are wrong, or 3I Atlas has optical characteristics that are unlike any object in our solar system. The spectral mapping data from Ferric is the basis for some of Loeb's most remarkable assertions. The enormous carbon dioxide coma, which stretches for nearly 250,000 miles from the nucleus, shows a level of activity that defies conventional models of outgassing. Loeb points out that such a large amount of gas production from a small nucleus would require either incredibly high levels of activity or mechanisms that spread the sources of gas over a much larger area than traditional comet models assume. His take on the debate about water detection demonstrates the careful method that defines his analysis. Initial observations from SWIFT indicated a significant production of water vapor based on detections of the hydroxyl radical, but later mapping by Spherex found water signatures to be well below the limits of detection. Instead of rejecting either finding, Loeb combines them into a single, logical story. 3I Atlas might have water ice in its core, but surface processes are stopping it from sublimating efficiently, which leads to the observed difference between the expected and detected amounts of water. Where Loeb's analysis becomes truly contentious is in his investigation of what he calls technological hypotheses for the behavior of 3I Atlas. Taking inspiration from the unexplained acceleration of one IOMU-MUA, he considers whether conventional physics can completely explain the visitor's extensive carbon dioxide coma and its strange brightness characteristics. His calculations indicate that purely natural outgassing might not be enough to account for the huge gas cloud, which leads him to wonder if other energy sources could be contributing to the observed activity. The hypothesis of self-luminosity is perhaps Loeb's most daring proposal. If 3I Atlas has internal energy sources other than just solar heating, whether from radioactive decay, electrical events, or more unusual mechanisms, it could sustain activity levels that natural sublimation processes cannot account for. Such internal energy could fuel the large-scale production of carbon dioxide while remaining impossible to detect with standard astronomical observations. Loeb's analysis of the trajectory adds another layer of curiosity to his technological hypothesis. He points out that the path of 3I Atlas through our solar system has geometric features that make it ideal for observation from Earth, almost as if the path was planned for the greatest scientific benefit. While this could certainly be a matter of chance, as the universe is full of cosmic coincidences, Loeb suggests that we should at least think about whether such a perfect geometry could be a sign of deliberate navigation. The proposals for an intercept mission that Loeb has co-written are perhaps his most tangible contribution to the science of 3I Atlas. In collaboration with experts in spacecraft trajectories, he has laid out detailed plans for redirecting NASA's Juno mission toward a meeting with the visitor in March 2026. These plans include specific timings for engine burns, delta-V needs, and the capabilities of scientific instruments that could provide unprecedented close-up data on an interstellar object. Yet even Loeb admits that his more unusual hypotheses are speculative. His essays consistently present technological explanations as possibilities to be explored, not as firm conclusions. The scientific method requires that we look at all possibilities that are consistent with the observational data, even those that question our standard assumptions about what interstellar debris should be like. The media's reaction to Loeb's analysis of 3I Atlas has been predictable, with headlines about potential hostile technology that twist his carefully worded speculations into sensational stories about alien visits. This kind of reporting misrepresents both Loeb's actual points and the scientific process of testing hypotheses. Loeb suggests technological scenarios not because he is convinced they are true, but because they are testable alternatives to conventional explanations. His method for studying 3I Atlas is part of a larger philosophy on how science should handle unusual data. Instead of trying to fit observations into existing theoretical models, Loeb recommends expanding those models to include possibilities that might at first seem far-fetched. This approach has a basis in history. Many groundbreaking discoveries in astronomy started with observations that did not align with conventional models. The testing procedures that Loewe suggests for telling the difference between natural and technological hypotheses offer a way to solve the mystery of 3I Atlas using observational data instead of theoretical bias. High-frequency photometry could show if the object's brightness changes in a way that is consistent with artificial lighting. Spectroscopic observation could find emission lines that point to unusual chemical processes. Close-up encounters with spacecraft could measure properties that are impossible to ascertain from astronomical distances. Loeb's work with mainstream observational teams shows his dedication to evidence-based research rather than speculative thinking. His estimations of size and chemical interpretations are based on the same data that other researchers use, although his readiness to consider unconventional explanations often results in different conclusions. The scientific discussion about 3I Atlas has been made richer by this variety of viewpoints. Even when these viewpoints cause controversy, the time constraint on observing 3I Atlas makes Loeb's arguments about hypothesis testing more urgent. With only a few months left before the visitor vanishes forever into interstellar space, the chance to collect definitive evidence is quickly running out. If technological hypotheses are to be examined, the examination must take place now, during the short time when 3I Atlas is still within reach of our most powerful instruments. As the solar conjunction gets closer and the chances for observation decrease, Loeb's analysis is both a scientific contribution and a philosophical statement on the essence of astronomical research. His willingness to consider possibilities that other researchers shy away from brings up a bigger question about how science should deal with genuinely strange data. Should we give priority to conventional explanations that align with existing models, or should we stay open to explanations that could transform our understanding of what is possible in the universe? The debate over 3I Atlas might in the end be remembered not for the specific hypotheses it brought forth, but for the scientific approach it demonstrated. The delicate equilibrium between sound skepticism and true open-mindedness is what enables science to advance beyond the limits of current knowledge. Part 14. What could confirm or falsify theories? Next, the upcoming solar conjunction of 3I Atlas sets up a natural test of astronomical patience. But its reappearance in December will set off one of the most comprehensive observational efforts in the history of studying small celestial bodies. The examinations that lie ahead for our interstellar visitor are nothing short of a scientific ordeal by fire, where different hypotheses about its nature will be judged by the ultimate arbiter, observational evidence. The spectroscopy after perihelion is crucial for solving the chemical puzzles that have characterized 3I Atlas since it was first seen. If the behavior of this visitor is dictated by natural sublimation physics, then the ratio of carbon dioxide to water should change in a predictable way as it travels away from the Sun's gravity. The temperature of the nucleus would have reached its peak during the unobservable passage through perihelion, possibly melting through any insulating surface layers that might have prevented water vapor from escaping earlier in its approach. Spectra from December and January should reveal an increase in water emission if such suppression mechanisms are at play. On the other hand, if the dominance of carbon dioxide continues without change through perihelion, it would point to either a composition that is genuinely poor in water or mechanisms that keep the chemical imbalance regardless of temperature. Such a continuation would defy conventional models of cometary volatile evolution and could potentially lend support to more unusual explanations for the behavior of 3I Atlas. High-frequency light curve observations are another vital test for the competing hypotheses. If 3I Atlas is a standard nucleus experiencing normal outgassing, its brightness should exhibit predictable patterns linked to its rotation and jet activity. Most active comets show changes in brightness over periods of hours to days as rotating features on their surface alternately face toward and away from the Sun's position. The lack of such changes would suggest either an unusually consistent surface composition or a viewing angle that reduces rotational modulation. More strikingly, any sign of artificial lighting or non-thermal emission would appear as brightness variations that do not correspond with solar heating or geometric factors. Such signs would be exceptionally hard to replicate through natural means, offering what could be conclusive evidence for more exotic explanations. The photometric monitoring during December and January will effectively keep 3i Atlas under constant watch, documenting every change in brightness that might disclose its true nature. Resolved imaging campaigns with Hubble and large ground-based telescopes will track the changes in the coma's shape as 3i Atlas reacts to its close encounter with the Sun. Models of natural outgassing foresee specific patterns of dust release and tail formation that should become more noticeable as the visitor moves away from the Sun's position. The shape, orientation, and growth rate of any tail structures will provide thorough tests of whether 3i Atlas adheres to conventional cometary physics or follows a different set of rules. The observations near Mars on October 3rd present a special chance to examine 3i Atlas from an extraterrestrial viewpoint during the time when Earth's observation is impossible. If the high-rise camera on the Mars Reconnaissance Orbiter can take pictures during the close approach, the data would offer vital information on the structure of the coma and patterns of activity during the period of maximum thermal stress. The viewing angle from Mars will be entirely different from the perspective on Earth, which could reveal asymmetries or directional effects that are not visible from our location. Unplanned spacecraft observations could offer the most conclusive tests of the nature of 3i Atlas. The encounter with the Psyche mission in September, the observations by JUICE in November, and potential imaging by OSIRIS-APEX in late 2025 each present the chance for close-up measurements that ground-based telescopes cannot make. Data from spacecraft could resolve the nucleus directly, measure interactions with magnetic fields, and detect particle emissions that would differentiate between natural and artificial origins. The follow-up observations by the James Webb Space Telescope will take infrared spectroscopy to new levels of sensitivity and spectral resolution. Webb's capability to detect minute amounts of organic compounds, measure isotopic ratios, and map the three-dimensional structure of gas emissions could provide the chemical proof needed to distinguish between different formation scenarios. If 3i Atlas displays isotopic signatures typical of the early galaxy, it would back the hypothesis of a thick disk origin. Unusual isotope ratios might suggest processing by strange mechanisms during its journey through interstellar space. SphereX's ongoing mapping of the carbon dioxide cloud will test whether the large emission area expands, contracts, or stays at its huge size as 3i Atlas travels through various solar environments. Models of natural outgassing predict specific connections between the distance from the Sun and the size of the coma that should be observable if conventional physics controls the visitor's behavior. Perhaps most crucially, any detection of non-gravitational acceleration would give vital information on the mechanisms that are driving the activity of 3i Atlas. The precise astrometry required to find such effects needs months of continuous tracking, comparing observed positions with models based purely on gravity. If anomalies in acceleration are found, their size and direction could help distinguish between conventional outgassing effects and more unusual sources of force. The combination of multiple observational methods, chemistry, dynamics, morphology, and photometry will lead to conclusions that no single technique could arrive at on its own. Natural explanations for the behavior of 3i Atlas make specific, testable predictions about how these different observables should be related. Technological hypotheses predict different patterns of correlation, creating decision paths where observational evidence can lead us to the truth. The observation period from December through March is humanity's last chance to understand this particular interstellar visitor. After that, 3i Atlas will dim beyond the detection capabilities of even our most powerful telescopes, taking its secrets with it back into the cosmic depths. The observational tests that are in store for our visitor represent both a scientific opportunity and a scientific duty. The chance to add another essential piece of data to our understanding of the universe, and the responsibility to pursue that understanding with thoroughness and an open mind. The universe has brought 3i Atlas to our cosmic doorstep for reasons we may never fully grasp. Our reaction to this gift will decide whether we come away from this encounter with more knowledge or just more mystery. Part 15. The Bigger Picture. Preparing for the next one. The tale of 3i Atlas is about much more than just a single interstellar visitor speeding through our solar system. It marks the start of a new age in astronomy, where the space between stars is no longer seen as an empty expanse, but as a populated area filled with wandering worlds and cosmic fragments. As we try to comprehend this specific visitor, we are also setting the stage for studying many more that are expected to be discovered in the years to come. The Rubin Observatory's Legacy Survey of Space and Time is set to completely change our understanding of interstellar populations through its immense statistical capability. When it begins full operations in 2025, Rubin's 8.4-meter mirror and 3.2 gigapixels camera will survey the entire southern sky every 3 nights, reaching levels of sensitivity that far surpass those of current surveys. Theoretical calculations indicate that this cosmic inventory could find anywhere from 0 to 70 interstellar visitors per year, depending on the actual size distribution and activity patterns of the galactic debris population. The shift from isolated discoveries to statistical samples will fundamentally alter how we conduct the science of interstellar visitors. Instead of viewing each object as a singular puzzle, we will start to see patterns, connections, and population trends that show the underlying physics of how planetary systems form and evolve across the galaxy. 3i Atlas, along with Oumuamua and Borisov, will be the reference data for this new statistical method of studying alien debris. The European Space Agency's Comet Interceptor mission is humanity's most ambitious effort to get ready for the next interstellar visitor. Planned for launch in 2029, this groundbreaking spacecraft will be positioned at the gravitationally stable Lagrange point L2, about 1.5 million kilometers from Earth, where it will be on standby for targets of opportunity. When the next interstellar visitor comes and statistical forecasts suggest it is just a matter of time, Comet Interceptor could change its course to an intercept path within months instead of years. The design concept behind Comet Interceptor recognizes the main difficulty in studying fast-moving interstellar visitors. We must be prepared before they show up, not rushing to react after they are found. The spacecraft will be equipped with a range of instruments specifically designed for high-speed encounters with pristine objects, including cameras that can resolve surface details, spectrometers that can analyze composition during short flybys, and dust analyzers that can collect and study the actual material shed by interstellar visitors. The quick response system being created for interstellar visitors has uses that go far beyond just pure science. The same survey systems that find cosmic travelers also watch for potentially dangerous asteroids, creating a synergy between planetary defense and interstellar research. The methods being improved for tracking 3i Atlas, such as rapid orbit determination, coordination between multiple observatories, and flexible telescope scheduling, will be extremely valuable for dealing with any future impact threats. The challenges of engaging the public about interstellar visitors demand a careful mix of scientific accuracy and responsible communication. Every new discovery leads to media speculation about alien origins, which creates chances for both education and the spread of misinformation. The experience with 3i Atlas has shown how important it is to provide clear and immediate scientific information that admits to real mysteries while steering clear of sensationalized interpretations that can mislead the public. The innovations in data processing developed for 3i Atlas have set new benchmarks for coordinated astronomical observations. The real-time sharing of data from Hubble, Webb, spherics, and ground-based observatories has led to unprecedented collaborations where the capabilities of each instrument enhance the others. This cooperative framework offers a model for studying future interstellar visitors, making sure that we get the most scientific value from each brief encounter. The partnerships between industry and academia that were formed during the 3i Atlas campaign have created new models for observing targets of opportunity. The traditional astronomical practice of carefully planned, peer-reviewed observing programs has turned out to be too slow for studying the rapidly changing nature of interstellar visitors. Instead, we have created quick-response procedures that can retask major facilities within days of a discovery, turning competitive telescope time into collaborative scientific platforms. The theoretical basis for understanding interstellar visitors has grown significantly since the discovery of Oumuamua, now including knowledge from planetary formation theory, astrobiology, and even speculative physics. 3i Atlas has contributed the aspect of carbon dioxide chemistry to this framework, painting a more detailed picture of the possible chemical environments where planetary debris can originate. Future visitors will test and improve this framework, possibly uncovering formation processes that do not occur in our own solar system. The philosophical questions raised by the study of interstellar visitors go beyond astronomy and touch on fundamental issues about the nature of planet formation and the abundance of life in the universe. If the chemical variety we have seen in just 3 visitors is representative of the true range of planet-forming environments, then the galaxy contains a vast collection of different chemical formulas for creating worlds. Some of these formulas might be conducive to the development of life, while others might result in environments that are completely inhospitable to biological processes. The technological progress spurred by the science of interstellar visitors has sped up advancements in several areas. Better spectrometer sensitivity, quicker image processing algorithms, and more advanced orbital mechanics software all benefit from the strict requirements of studying faint, fast-moving objects. These improvements will boost our ability to study not just interstellar visitors, but the entire range of small body populations throughout the solar system. The international collaboration that 3i Atlas has fostered serves as a model for tackling scientific problems that go beyond national borders. When the universe presents phenomena that demand a swift, coordinated reaction, the astronomical community has shown a remarkable capacity to put aside territorial issues and concentrate on common scientific objectives. This spirit of cooperation will be crucial as we get ready for future interstellar encounters that might happen with even less warning. The educational effect of discovering interstellar visitors has already started to change how we teach planetary science and astrobiology. Students who are learning about planet formation now study examples from other star systems, not just our own. The chemical diversity shown by 3i Atlas and its predecessors gives tangible proof that planetary environments can be vastly different from the Earth-centered examples that used to be prevalent in textbooks. As we get ready for the next interstellar visitor, the insights gained from 3i Atlas are not just about technical abilities, but also about the intellectual frameworks needed to understand genuinely alien phenomena. We have found that our theoretical models, which were developed based on examples from our solar system, might not be sufficient for understanding material from other stellar environments. The next visitor might challenge our assumptions in ways we have not yet foreseen. The cosmic viewpoint that comes from studying interstellar visitors is both humbling and inspiring. We inhabit a galaxy where planetary debris frequently crosses the lines between star systems, creating a slow but continuous exchange of material that links distant worlds across light years of space. 3i Atlas is just one small part of this vast cosmic network, but by studying it, we can see the complex patterns that hold our galaxy together. The universe continues to send us these messengers from the vastness of space. Each one brings news from regions of space and time that we can investigate in no other manner. Our reaction to these cosmic presents, the science we gain from brief meetings with wandering worlds, will shape how well we comprehend our position in the galactic community. As we observe 3 Atlas vanish into the blackout of the solar conjunction, we are not simply losing sight of a single visitor. We are getting ready for a time when such visitors will be a common feature in our astronomical view. When the space between stars changes from a mystery into a familiar area, filled with samples from 1,000 different worlds, the next messenger is already out there, somewhere in the cosmic darkness, on its own ancient path toward our solar system. When it comes, we will be prepared. Thank you for sharing this time with us tonight here on the Sleepy Explorer. If you found this journey enjoyable, please remember to subscribe so you can drift off with us once more on the next adventure. For the time being, we wish you a tranquil night's sleep. Good night, and thank you for tuning in.